So thanks all for tuning in. This is a second recording of topic number two, flexure capacity. So topic number two will be flexure capacity, focus on analysis and design of beam and one-way slabs. As we mentioned before, going to be covered by our textbook from chapter 2, 3, 4, and 5. And in-class lecture will be 6 lectures to cover this topic. So strength analysis of beam using ACI 31819. This is going to be our focus today. During the last few lecture and recording, we learned how to calculate the cracking moment, how to calculate the elastic stresses in concrete and steel, and also how to calculate the nominal or nominal capacity of beam under flexure or flexure nominal flexure strength. So here we're going to learn a lot how ACI 31819 approach strength analysis of beams. So first of all, the history of design code from 1900 to 1960s, all the codes were based on working or service load. So it's basically you take you let's say have steel and concrete, you take huge factor of safety and use only allowable stresses. So you don't allow us when you design the concrete to reach the maximum compressive strength of F prime C or steel to even yield. So you take factors to reduce F prime C um, and also the steel stresses. So use reduced concrete stresses and reduced steel stresses called working stresses. Those methods are very important because now we design fluid filled structure like water tanks using WSD or ASD because basically you don't allow it to crack. We use it partially in calculation of deflection. We use it for checking stresses on in cross sections in pre-stressed concrete, and it's really similar to the way that we calculate the stresses in the previous recording. The allowable stresses will be you limit, for example, if you have a steel of F yield of 60, you take factor of safety and use that as your allowable stresses. And if you have a compressive strength of concrete of 4,000 psi, you actually use even 14 or 1500 psi for design. 1963 and moving forward, USD strength design started to gain attention, and it's more rational than working load, provide more realistic estimation of safety. So actually you design where steel yields and concrete approach F prime C, so you can predict what type of failure that you can have, brittle failure as concrete concrete crushes, or steel yielding and previous multiple cracks. So in this case, we use factor for load as we discussed before. So the loads from ASCE is actually increased by a factor for dead load and live load. When you remember from topic number 1.2 for dead load and 1.6, this is 1.2 for dead load and 1.6 for live load. You increase the load side and you also decrease the strength side by a factor called resistance reduction factors. And we're going to get familiar with those two sides of the equation here. Topic 1 covered it very well from external loading. The topic 2, 3, and 4 will cover it for moment. So it's going to be MN. You can cover it for shear VN and for axial load PN. And after that, we're going to reduce it by resistance factors, which is going to be the focus of this lecture, how to get to the phi value. So as you know, here is a stress strain curve for different type of concrete based on compressive strength. And we covered very well during the last recording how to calculate the nominal stress, especially understanding how to construct with stresses or stress distribution and how to calculate forces using Whitney block. So concrete is assumed to crush at 0.03. This is the main assumption now. As you can see here, concrete is assumed to crush at this level. You are going to replace the nonlinear portion or the variation here with uniform distributed block called Whitney stress block. And this distance A will be equal beta 1C, which can be according to equation from ECI 22.2.2.4.3. And here is the equation. If you have prime C less than 4,000 psi, you always use beta 1.85. And you can see here, if you less than 4, use beta 1 of 0.85. If you actually use, if it's more than 4,000 psi, you use this equation. Beta 1 is equal to 0.85 minus prime C minus 4,000 divided by 20,000, and use here a prime C and psi. And this also has to be limited to 0.65. You cannot go lower than 0.65. So as we discussed before, design flexure strength is given by Feynman. Feynman is actually what's called ultimate strength. We get familiar how to calculate Mn last recording, but now we're gonna know how to calculate the phi value. So here is the same cross section. You have width of B, area steel AS. You have depth, structure depth from the top compression fibers to steel fiber, centroid of steel fiber as D. You construct Whitney block by A distance, and the height will be 0.85 F prime C. So the total area of compression C capital is 0.85 F prime C times area. In this case, area is B times A, and act at the middle of the block. So at A over 2 distance from the top. Tension will be equal AS if yield. Act at the centroid of the steel, and the arm will be the distance D minus A over 2 when you calculate Mn. So gain C equal T, assuming steel yield, AS time F yield equal 0.85 F prime C AB. From here you can get A as AS F yield divided by 0.85 F prime C B. Rho is what's called reinforced ratio. This is the area of steel divided by the B, the width of the cross section, and the structure depth D. So if you want to use AS in this equation, replace the AS in this equation by rho BD, you're going to have, let's say, rho BD. The B will be cancelled, and you'll end up rho F yield D divided by 1.5 prime C, another way to get to the A value. Remember, strains in this epsilon S or epsilon T, sometimes epsilon S or epsilon T, is the strain in the rebar at yielding. So F yield divided by ES is 60 KSI divided by 29,000 KSI, which is 0.0207 strain in the and you need to make sure that you actually yielded, because your assumption here assume that steel yielded. So let's recap again. You know that we mentioned before that C equal A divided by beta 1, or A equal beta 1C. So if you want to create the distribution of strain or strain diagram, you will achieve here strain of epsilon Cu, which is at crushing 0.003, and will reach to 0 at distance C, which is equal A divided by beta 1. This distance will be D minus C, and this will be epsilon T, or a strain in your reinforcement. Sometimes we call it epsilon S too, based on the different textbook. So 0.85 F prime C AB equal AS field, A equal AS field divided by 0.85 F prime CB, or also equal to beta 1 C. So C, after you calculate A, you can calculate C as A divided by beta 1. If you take trigonometry and ratios, you will have epsilon T divided by epsilon Cu, which is 0.03, going to be equal D minus C divided by C. Rearrange and get epsilon T, it's going to be D minus C divided by C. You have all those values, D and C, times 0.03. And even from there, you can verify if your steel is yielded or not and your assumption is correct or not. So let's calculate this very quickly using example number 1. In example number 1, I'm asking you to calculate value A, value C, and value epsilon T. So it's like one step from the previous recording, knowing that if yield is 60,000 psi and if prime C is 3,000 psi, area of steel is 3 inch square, width of the cross section is B equal 14, depth of the cross section D equal 21, and here is a distribution of strain distribution where steel concrete reach always 0.03, while C value is here and this D minus C value is here, and this is a strain epsilon T, which is 0.03 D minus C divided by C. Let's start calculating. So first one, A is given in equation as AS F yield divided by 0.85 F prime CB, which is from compression equal tension, capital C equal capital T. AS given as 60 KSI. Sorry, F yield 60 KSI, AS is 3 inch square. F prime C is 3 KSI, and B is 14, as you can see here. This is B. You gotta get A is 5.04 inches. You know that the concrete is 3,000 psi, so beta 1 is 0.85 based on the equation that I showed earlier. So see now you can calculate it as 5.93. Now, if your C is 593, you can calculate epsilon T as 0.03 times D minus C divided by C. D is 21. C is 5.93. We just calculated C small divided by C small. 5.93 times 0.03 equal 0.0762. Yielding epsilon T yielding is actually 0.00207, which make it very we can conclude that actually its yield is like so 3 times the yield, almost 4 times the yielding strain. So this rebar yielded, so your assumption here is correct. Okay, let's just to brainstorm. The less C that you're gonna get, the more strain you're gonna get in the rebar. However, the larger C you get, smaller strain. Okay, here I'm trying to show you a few concepts. The first one is balance section, tensile control, ductile section, compression control, brittle section. And the first video are showing that section called tension controlled ductile section, where this section is actually designed so the steel yields first before concrete crushes, so you can have multiple cracks generated and large deformations or deflection generated before the total failure of the cross section. So as you can see here, multiple cracks generate along the length of the girder as we load it, and these ductilities that we achieve actually can give you a warning sign to evacuate. However, in compression control section, brittle section, concrete crushes before steel yields. You may have issue during the recording that those video will not be displayed. As we so to just recap again, in tension control, steel will yield or even exceed a certain level of strain that we're gonna show later before concrete start to crush to give you sign of warning and the ductility you want. And this section also used to be called in different codes under reinforced section. And the compression control, concrete will crush before steel yields, which is brittle and is not desired by the code. So you have balance section, you have tension control section, you have compression section. So the balance section is really good concept, that the balance section is section that has steel ratio such that the steel reach yield strain, F yield divided by ES, when concrete attain strain equal to 0.03. So concrete will crush same time, same moment as steel yields. And this ratio can call it row balance. Okay, row balance. Concrete member with less than row balance, less than row balance, you'll have less reinforcement than row balance. Those reinforcement will yield earlier than concrete crushes and will fail in ductile manner, so steel yield before concrete crushes. However, if you use more reinforcement, so your steel ratio is more than row balance, you will fail in brittle manner. Ductile section called tension control, brittle members are called compression control. So let's focus on this red balance section. So the balance section, if you see the strain diagram, you reach the crushing at 0.03 at the same moment steel yield. So you put here epsilon yield, if yield divided by epsilon s, you have those distance, right, or those strains, and you also have D, you easily can calculate C at balance, C balance. Okay, so C balance divided by D, C balance divided by D will equal 0.03 divided by the summation 0.03 plus epsilon yield. Epsilon yield. If you rearrange it, you're going to be 0.03 divided by 0.03 plus F yield divided by 29 to the time to 10 to the power 6. So C balance actually can be calculated as 87,000 divided by 87,000 plus F yield times D. So it's only a function of the depth of the cross section and the type of steel that you are using, so F yield. You also have an equation before that A equal AS F yield divided by 0.85 F prime CP, or rho F yield D divided by 0.85 F prime CP. We did derive this before. So C equal A over beta 1. So we can now use the same equation, C equal rho F yield D divided by 0.85 beta 1 F prime C. if you those are both at balance, so because you are using row balance, so row balance here, if you make C balance equal C balance from those two equations, you can get row balance as 0.85 beta 1 F prime C divided by F yield times 87,000 divided by 87,000 plus F yield. And in this nice equation, it's only function of F prime C and F yield, since beta 1 is also a function of F prime C. So you can actually get row balance very quickly from this equation if I give you the ratios. And from row balance, you can get AS at balance, which is going to be row balance BD. So in tension control section, this is diagram relationship between what's called strain in the horizontal axis and phi in the vertical axis, which is what we are looking for. So according to ACI section 221.2.2, members to steel is greater than the yield plus 0.03. If you are using if yield of 60, it's approximately 0.05. If your strain that you calculate is greater than this number, you are tension controlled section and considered to be fully ductile, and your phi value in this case just 0.9. Okay. And steel will yield before concrete crushes, deflections are large, and there is warning of failure. Okay. If you do compression control is this region. So this is tension control, this is compression control. This happens when, according to ACI 21.2.2, remember those steel strain is less than epsilon yield when concrete reach 0.03, called compression control, or to be brittle. Concrete crush before steel yields in this zone, and your phi value will be 0.65. Deflection are very small, there is no warning signs. Actually, the code is not allowing you to design any flexion member, beams or slab under compression control. Between the two, between epsilon T equal epsilon yield or epsilon T equal epsilon E plus 0.03, you are in transition zone where your phi value will be by interpolation. Also, need to know that the code will not allow you to design any cross section for beams or one-way slabs or other flexion members where epsilon T is, or epsilon S, less than 0.004. So in this case, when section is in transition zone, because it's going to be almost here, you have to interpolate to find the phi value. And you also need to know that if you have grade 60 steel, your strain epsilon Ty is almost 0.02. Get the phi values here. We know that if you are more than epsilon Ty plus 0.03, your phi value is 0.9. We always try to have tension controlled beams and slabs as 0.9. In the shear and torsion with 0.75. In the column is 0.75 or 0.65. And you will see the bearing concrete also you get 0.65. So it's this phi value is lower always if your failure mode is toward brittle failure, and it's higher if your failure mode is toward ductile failure. And here, in order to avoid you time consuming time during solution of any problem, table 21.2.2 will give you the equations that you need for transition zone. So if you are less than yielding, 0.65. If you are more than yielding plus 0.03, you are 0.9 as phi value, and if you are in the transition zone, your equation is 0.65 plus 0.25 times epsilon T that you calculated minus epsilon Ty, which is the yielding 0.00207 if you are grade 60 steel, divided by 0.03. You now can conclude that if you calculate AS at balance or row balance, if you increase then steel, it's not in your favor because steel will not yield, concrete will crush first. but you need to reduce that rho value and AS to be less than rho balance or AS balance, which make you, can I actually reduce it a lot? No, the code actually in section 6.6.111 will give you a limitation of AS minimum, so you cannot make AS less than 3 square root of prime C divided by a field BWT, or 200 BWT divided by a field. BW actually is width of the web because it also applies to T sections. So T section, this is a B web. In rectangular section, B web is equal B. Okay, and you can also divide if AS minimum by BWD, which is the ratio, give you the reinforcing ratio rho minimum. So it's going to be 3 square root of prime C using PSI divided by FY, or 200 divided by FY, and this will give you actually the rho minimum. So if I'm where you, I calculate rho balance first, I calculate rho minimum, and I know that I have to be in between the rho balance and rho minimum, and most likely to be close toward the rho minimum. So in this example number 2, let's calculate determine ACI, design flexure strength, which is ultimate, not nominal. If yield is 60,000 psi and if prime C is 4,000 psi, cross section is 15 inch wide, 24 structure depth D, and 3 inch cover, and area of steel is total 4 inch square. You first need to calculate rho. Your rho in this case is 4 inch square divided by BWD. B is 15, D is 24, give you 0.011. Rho minimum, if you calculate it, going to be 0.03. Rho maximum 0.018. So you're actually in safe zone. So now you can actually go on step by step as we did before. A is equal AS F field divided by 0.85 F prime CB. It's going to be 60 KSI as a field, 4 inch square as AS divided by 0.85. F prime C is 4 KSI and B is 15. This is going to give you A of 4.71. If prime C is 4,000 psi, beta 1 will be 0.85. So C small is 8 divided by beta 1. And then in this case, A is 4.71, beta 1 is 0.85, so C is 5.54. Calculate epsilon T tension or epsilon S in steel, same terminology, is D minus C divided by C times 0.03 is 24 minus 5.54 divided by 5.54 times 0.03, give you 0.01. The strain is 0.01. This is way more than 0.05, or if epsilon Ty plus 0.03. So you are almost here. So if phi value is 0.9, as you can see on the board here. Now we calculate the moment. The moment is T times or C times arm. And in this case, T is AS field. Arm is D minus A over 2. D is 24. A is 4.71 divided by 2. Give me moment is 452.9 kip foot. Phi is calculated as 0.9. So phi Mn, which is M ultimate, will be in this case 389.6 kip foot. In example number 3, we actually using cross section of width 12 inches, depth total depth of 18, structural depth of 15, cover of 3, and reinforcement 4.68. Okay, so steel is almost 60 psi yielding, and a concrete prime C is 4,000 psi. So we need to recalculate A for this cross section using AS field divided by 0.85 F prime C, and this is going to be 60 times 4.68 divided by 0.85 divided by 4, which is F prime C, divided by 12, which is B, give you A of 6.88. You know, beta 1 is still 0.85 because your F prime C is 4,000 psi. C is A divided by beta 1, to give you based on A value as 6.88 and beta 1.85. C value, small c's value will be 8.09. Epsilon t will be d minus c divided by c times 0.03. So d is 15, c is 8.09, and c, so you can calculate the stresses here, strains here as 0.0256. Actually, this is more than the yield, epsilon yield, but it's less than 0.04, the limit for ACI. So you cannot, ACI cannot allow you to design less than 0.05 strain in the steel, even you are still in transition zone. So actually section is not ductile and may not be used according to ACI 7331. Last example here before we conclude, another cross section, the width is 10 inches, the depth of 18, structure depth D is 15, cover 3, and steel 3-inch square. And if you have ACI, if you have steel still, if yield is 60, and if prime C as 4,000 psi, you repeat the equation, A equal AS if yield divided by 0.85 if prime CB. If yield is 60, assuming it's yielding, AS is 3-inch square, if prime C is 4, and B is 10, give you A equal 5.29 inches. Beta 1 is 0.85 because concrete is 4,000 psi. C is A divided by beta 1, it gives you 6.22. Epsilon t in this case will be D minus C divided by C times 0.03, which can lead you to 50 minus 6.22 divided by 6.22 times 0.03. It gives you 0.00723. In this case, it's more than yield, so you are actually good, and also more than epsilon of 0.004. But you are not more than if epsilon t y plus 0.03, which is approximately to be 0.05, right? So you are less than 0.05 almost. At the same time, you are more than 0.04, so section can be used, but you need to calculate phi now. Phi will be based on this equation from ACI table 21.2.2. So what you need to do now is put here your strain 0.043, and the yielding will be 0.00207. I just crossed out this equation because this is from ACI 31814, and it's replaced by this equation in 2019 version. And now you can get your phi value is 0.83. Now your moment Mn is still C or T times R. So T is, because yielding actually is yielded 3 times 60, and D is 15, structural depth. A divided by 2 is 5.29 divided by 2, giving moment Mn equal 185.3. You get phi value 0.85, but you are not looking for Mn, you are looking for phi Mn or M ultimate, which is going to be phi times Mn. Phi is 0.83, Mn is 185.3, so you end up having moment of 153.7 that can be resisted by this cross section. Thank you for tuning in. I'm looking forward to the next recording.